All right, so today we want to start with the blood, composition of the blood and its functions. But before I do that, do you have any questions from last week's lesson? Any questions from last week's lesson?
No, thank you.
So far, so good. Okay, all right. If you have other questions, you can ask during the when we go through the practice questions as well. Okay, all right. So today we want to look at the blood and its composition, what the blood is made up of. So the blood is composed of the liquid part, which you call the plasma, all right, and the formed cells. So you have plasma and the formed cells. And the plasma forms about 90 to 92% of, the water forms about 90 to 92% of the plasma, right? And then you have the dissolved gases like carbon dioxide, oxygen, and then you also have nutrients like glucose, fats, and amino acids, and so on, salts and proteins. Proteins in the blood or in the plasma, some of them are fibrinogen, albumin, immunoglobulins, and hormones, right? And then other nitrogenous waste like urea and what we call the uric acid, all right? So those are some of the waste products in the plasma. Okay. Now, when you say plasma, the plasma is made up of what we call serum and fibrinogen. So serum and fibrinogen, makes up the plasma, right? Now, fibrin or the fibrinogen, fibrinogen is what makes the blood clot. So when I say fibrinogen, this is what makes the blood clot, right? Serum does not clot. So serum will not clot, but fibrinogen will clot. So if you take out fibrinogen from the blood, then that blood is not going to clot. It's not going to clot. So that's something that you have to also note, right? Now, fibrinogen is an inactive substance in the blood. So what you have here, this fibrinogen is inactive. It's an inactive substance, right? Now, before it can cause the blood to clot, it becomes active. And the fibrinogen has to change to what we call fibrin. So fibrin becomes fibrinogen, which is the active form. So inactive, it has to become fibrinogen. No, sorry, I keep saying fibrinogen. It has to become fibrin. It has to become fibrin. And the fibrin is the active form of this protein. And this is what makes the blood clot. Okay, has to become active. So you can just keep that somewhere. Okay. Now, the blood cells that we have, there are 3 of them, as we all know. So you have the red blood cells, also known as the erythrocytes. Erythrocytes, right? Erythro means red. Erythro is red. And then the red blood cells, which we shorten it to be RBC, it contains hemoglobin. So it has hemoglobin in it, and hemoglobin has iron in it. Hem means iron, and globin means protein, right? So hemoglobin, iron plus a protein, that's what we call hemoglobin. And the function of the red blood cell is to transport oxygen. So that's the main function, to carry oxygen in the blood, oxygen transport, right? It also carries some amount of carbon dioxide, but just a small percentage, tiny. So the main function is to transport oxygen, right? So remember that if somebody has low amount of iron, then the person can have low levels of red blood cells, right? Low levels of RBC, and that's what we call anemia. So iron deficiency is one of the causes of anemia. So when you start your clinicals, remember that as well. You know, that there are so many causes of anemia, but this is just one of them. So, but for the purposes of this test, remember the function of the red blood cell, main function to transport oxygen. And then we also have the white blood cells, also known as the leukocytes. Leuko means white, and then cyte, cell, so white cells. There are different groups of the white blood cells, but the general function of the white blood cells is to fight infection. They fight infection. So that's the main function of the white blood cells, fighting infection, right? But then if you want to be more specific, you know, if you look at the individual groups of white blood cells, like the neutrophil is one of them, neutrophil, and they have the eosinophil, and have basophils, and have monocytes, and then lymphocytes. So all these are different types of white blood cells. Neutrophils, eosinophils, basophils, monocytes, and lymphocytes, right? They are classified based on how they stain, right? You have something called acid stain. You have something called basic stain. So depending on how they stain, that's how they classify them. So neutrophils, they don't stain at all, right? No staining. Eosinophils, they pick up acid stain. And the basophils pick up what we call the basic type of stains. So we call them basophils. So if you get a chance, go on the internet and look at the pictures of them. You see different colors, purple color for eosinophils and the basophils and so on. And the neutrophils appear like pinkish because they don't pick up the stain. Right? But the function of the neutrophils, the main function of the neutrophils is to fight bacterial infection, right? So if you have the neutrophils, this one here, this one will be, it will fight bacteria infection, bacteria infection. I'm going to write that here. But if you can remember the general purpose, that's fighting infection, that should be fine. If you do anatomy physiology, then you go into more specifics here. So if you see neutrophils, specifically, they fight bacterial infections. They fight off bacteria. Okay. So if somebody has high level of neutrophils in the blood, then it means that the person has bacteria infection. Okay. Then the eosinophils. Eosinophils, their main purpose is to they play a role in allergic reactions, so allergies, and they also fight off parasites. So we see the eosinophils. This one will be parasitic infections. They fight off parasites. And also allergic reactions, allergies. So the levels go up in allergic reactions, okay? And parasitic infections. Then the basophils. The basophils, they are also involved in allergic reactions. So they also go up in allergic reactions. No. They release what we call histamines that cause allergies. Okay. Then the monocytes. Monocytes, they are like scavengers. So they clear the site of infection. So once the neutrophils have fought off the bacteria, then they also come to the site to fight off infections. And then they can also clear cancer cells, right? So those monocytes, let's write that here. The monocytes, they are like scavengers. Monocytes. So they clear sites of infection. Okay. The monocytes. Then lymphocytes, if the levels go up, it means that the person has viral infections because they fight off viral infections. So if the doctor orders the blood count, these are the things that they look out for. Depending on which one goes up, then they can tell you have viral infection or have bacterial infection and so on. Okay. So those are the specific functions of each of these cells. But the general function, as you can see, they fight off infection, right? And then the last one is the platelets. So the platelets, remember that the platelets, the function is for clotting of blood. So blood clotting of blood, all right? And I want you to remember that these are not complete cells. No, they are not cells. The platelets are not cells. They are just fragments of cells. Cells are broken down, fragments of cells. Okay. So they're not going to have nucleus like the other ones. The other ones are full cells. So they have nucleus in them and so on. Okay. But platelets are fragments of cells. Very important to remember that part here. Okay. So this is the general function and the type of blood cells that we have. You know, and so if you have this idea, I think you should be fine on your test. Okay, good. Any questions on that? The blood and function.
Professor, I have a question.
Yes, please go ahead.
You mentioned that monocytes clear sites of infection. Does it matter what type of infection, if it's bacterial or viral?
No, it doesn't matter. It doesn't matter at all. They just come to clear things off. If cancer cells, they even clear cancer cells too.
Oh, cancer cell. Okay, thank you.
Yeah, they clear everything. Like they come there to, it's like come to mop up everything that is left in that site.
Okay.
Yes.
Thank you.
You're welcome. Yeah. Great. So this is the first part of the biology for today. We'll come back again to some of these, but I want us to delve a little bit into physics, because physics is part of the test. A lot of people, I know most people haven't done physics. You know, usually when I ask how many people have done physics, I don't get any number. So we'll take our time to go through physics today. You know, and these are basic concepts that will be asked on the test, which you should also know. So the first one I want to start with is introduction to what we call mechanics, movements, or motion and forces. Okay. So there are three laws that I want us to go through. And those are the Newton's laws of motion, right? So Isaac Newton came up with these laws that govern motion. You know, it's very easy to understand this concept. So the first law, let's look at the first law, and I have some explanations on the right side. So the first law says that objects at rest remain at rest, and objects in motion remain in motion in a straight line, unless acted upon by an unbalanced force, right? In other words, it's saying that if an object, let's say an object is on the table, if I put a book on the table, if I come back 100 years later or 1,000 years later, the book will still be on the table. It's still going to be on the table unless there's a force that pushes or acts on it. or pushes from the table. Or to stay there forever. That's what it's trying to say. You know, the same way if an object is moving, let's say someone is sitting in a bus, and the bus is moving, you move with the same speed as the bus, right? And if the bus stops suddenly, you continue to move with the same speed. You know, the only thing that will stop you will be, let's say, the windshield. That's the only thing that can stop the person. Or the person will keep moving forever. You know, something has to act on the person to stop. So that is his first law, right? So I put down some scenario on the right side, explanation of the law, which you can have on a test, right? And she was to say, well, this is first law, this second law, and so on. So example, the first law, as I have there, I said passengers in the bus move at the same speed as the bus. When the bus comes to a sudden stop, passengers will keep moving or thrown out in the straight path at the same speed and would only be stopped by the windshield, which will be the opposing force, right? The windshield will act in the opposite direction. The force acts in the opposite direction of the movement to stop the person. Okay. And then the book on the table will stay in the same place forever unless acted upon by an external force, such as a push or a pull, right? So that's the first law. Then the second law says that force is equal to the mass times the acceleration. Force is equal to the mass times acceleration. I want you to keep this somewhere. We'll be using it in answering questions as we go along. So when they give you the mass and acceleration, you should be able to find the force. Okay, you should be able to find the force. You know, we measure force in the unit called newtons, right? Force. The unit for force, unit, is newtons. Newton. We use N to represent the newtons, N. So that's a unit for force. Okay, they can ask that too. So what's the explanation of this formula or law? So what it's saying is that the force on an object is directly proportional to its acceleration and the mass. So it's a direct proportionality. That means that as the mass increases, the force will also increase. As the acceleration increases, the force will increase. And so the change is the same direction. If it goes down, both go down. If it goes up, then the force also goes up. That's what this means, direct proportionality, right? Between mass acceleration and the force, right? Then point number 2. Now, this means that as acceleration increases on a fixed mass on an object, its force also increases. Same applies to the mass. Okay, that's the direct proportionality as I explained. And then point number 3. So for a given force, the acceleration is inversely proportional to the mass. Inversely proportional to the mass. You know, in other words, if you increase the mass, in other words, increasing the mass will decrease the acceleration for a particular force, or a given force. Okay. So for any given force, if you increase the mass, that means that acceleration will decrease. It means the object is going to move a little, it's going to move slower, right? And so on. That's between the mass and the acceleration. They're inverse. One goes up, the other one goes down for the same amount of force, right? So that is second law. Then the third law. So the third law says that for every action, there is an equal and opposite reaction. For every action, there's an equal and opposite reaction, right? So in other words, if this is a wall, if I push this wall with a force of 3 newtons, this wall will also push me back with the same force of 3 newtons. They are equal, but in opposite directions, right? if the force I'm using is greater than the force which the wall is pushing me, that means I'll break the wall. So it has to be balanced. The same way, if I'm standing on the ground, my weight is the force, right? If my weight is greater than the force which the ground is pushing me up, then I'm going to bounce, right? If my force is greater, then I'm going to sink. But the force is greater, from the ground is greater, then it's going to throw me away. You know, but I'm standing stable because it's balanced. Yeah, the force is acting in opposite directions, and they are equal. Okay. So I put an explanation here of the third law, some of the scenarios that you can have in a question. All right. So if you push the wall also pushes you back with the same force, acting in opposite direction. And then 2, as you stand on the floor or ground, you do not sink because the ground is pushing you back with the same force in the opposite direction. So if you see these scenarios, this is the third law. The third law. Okay. Right. Good. So now let's apply it to some questions here. You know, how do you apply this to questions? I want you to read the first question to see. It says that the engine of a train of mass 800 kilograms, which is traveling along the straight horizontal road, is producing a force of 1200 newtons. Assuming that there are no forces acting, resisting the motion, calculate the acceleration of the train. We want to calculate the acceleration of the train. All right. So when I read this question, the mass is given. The mass is given kilograms, right? And then this is producing a force of 1200 newtons. So I know the mass and I know the force, right? I can easily find the acceleration. Okay. So we know that force is equal to the mass times acceleration, as we have here. Force equal to mass times acceleration, right? So since I know the mass and I know the force, I can just set up the equation here, you know. Here I rearrange first, but if you're not too sure of yourself, you can always do the regular algebra. 1200 is equal to 800 times acceleration, all right? And then you divide, forget about this, I put the wrong numbers here. I put the wrong numbers here, so this should change. So you divide by 800, and then divide this by 800. So this should not be the correct one here. And then you can reduce the lowest terms. So A will be equal to 800 divided by that. So the zeros will cross out. And I have 12 over 8. If you reduce still to lowest terms, that would be 2 here will be, so 4 here will be 2, 4 here will be 3. So you have 3 over 2. So it means acceleration will be equal to 1.5 meters per second squared. Okay, so this is the answer that we should get. Okay. So it's all based on using the formula force is equal to the mass times the acceleration. Force equal to mass times acceleration. Okay. So if you get a question like this, you should be able to apply this concept. Okay. Any question on this particular one? Okay. Okay. So the second one is also very similar. We have a van is pulling a car of mass 1500 kilograms along a straight horizontal road. The only force which acts on the motion of the car is the tension in the horizontal tow bar. Calculate the acceleration of the car when the tension is 750 newtons, right? So tension is the same as like the force. If you're pulling something, tension is like this, the force. So we're given 750 newtons as a force. You know the mass. It's a calculated acceleration. So that's very similar.
So, Professor, tension and the force are the same thing?
Say that again.
The force, like the F, and the tension, it is the same thing?
Yeah, force and tension the same, yes.
Thank you.
Yes, same thing. Okay. Remember, it's just like a rope. If you hang something, if you pull in, let's say a car is here, and you're pulling, you know, the force, the tension in this is a force.
Okay.
Yes, good. All right. So I think I ended up changing the two things here when I was typing. So this should be 750 here. This is 750. I interchange my numbers. I put this then. So this is 750 here. You know, so this is correct for this one. So that's how you use the formula. You know. So I believe you see a question like this, you should be able to apply this formula. Okay. Great. All right, so let's look at more information. All right. Now, then, for every science course, there are some quantities that you have to know. You know, the quantities that are used. One of them is called scalar quantity, and the other one is called vector. So you have scalar and vector quantities. Right? When you say a scalar quantity, scalar, we are talking about quantities that have only magnitude. They have only magnitude, nothing else. Magnitude means size, right? Like you look at the size of what you're talking about, you know. And example of scalar quantity will be length. Where you have to know some of the examples of the quantities. Sometimes they ask which of the following is a scalar quantity and so on, or these are examples of scalar quantity. So examples of scalar quantity will be length, area, volume, speed, mass, density, temperature, pressure, energy, what we call entropy, and work and power. These are all scalar quantities. You just have to know the size of that quantity, right? Only the size is important, nothing else, right? So 2 meters, if I say 2 meters, that's I'm only interested in the size. If 5 ml, I'm only interested in the size of the volume, right? Or I'm traveling at a speed of 2, if I'm traveling, let's say 2 miles per hour. That's my speed. And so on. I don't need to state anything else other than the size of what I'm talking about. Okay, so those are scalar quantities. So know some of these. Then the other one is called vector quantity. The vector quantity has both magnitude and direction. The two things go together. So when I'm talking a vector, I have to tell you the direction as well as the magnitude, right? So examples of that would be like what we call displacement and direction, right? Velocity, acceleration, momentum, force, electrical field, magnetic field. These are all examples of vector quantities, right? So if I'm talking about displacement, I'm going to add one more thing here so that at least you see under the scalar quantity. Let's add the word distance. It goes to the length, okay, but let's put the word distance here. Okay, but distance is different from displacement, right? Displacement. So displacement here, if I want to, example of displacement will be, if I say I traveled 2 miles west, this will be displacement. It's an example of displacement. 2 miles west or 2 miles east. I have to specify the direction. Okay. The same way speed and velocity are two different things. Now, when I talk of velocity, then I have to tell you my direction. So I'm traveling 2 miles per hour, let's say west. I have to specify that direction. Very important. Then we can velocity. So velocity and speed are two different things. Displacement and distance are two different things. For distance, I can just say I travel 2 miles. I don't have to tell you which direction I went. 2 miles, that's enough for displacement, for distance. Okay. So note the difference between the two things. The same with force. If I'm dealing with force, I have to tell which direction the force is acting, whether north, south, east, west, and so on, right? So those are some of the quantities that you should know of. You know, when they give you on the test, you should to say this scalar quantity, this is vector quantity, and so on. Okay. So scalar only point the magnitude. Vector, both direction and magnitude are important. Okay, great. So I put down food for thought. What's the difference between displacement and distance? You know, I just said that, right? So think about that again. All right. So we'll come back to talk about forces in the next section here after this one. All right, some important formulas to know when you're dealing with motion. This is similar to what you know in your math classes. Distance is equal to speed times time, right? Distance is speed times time. Some people would say rate times time, the same thing. So that's distance. Okay. Now, if it is displacement, then we have to say that displacement is the velocity times time. Velocity times time, that gives you what we call displacement. Velocity times time, right? It's similar to the distance. But since this is vector, you have to use velocity. Okay. Then when we talk about work done, we'll talk about work done. Work done is given by the force times the distance. So if you know the force, you multiply by the distance, the force moves through, you get the distance. Okay, so work is equal to force times distance. Okay. Then acceleration. Acceleration is equal to the change in velocity over the change in time. In other words, the rate of change of velocity. So think about your algebra where we have slope. Remember, slope is equal to change in y over the change in x. y1 minus y2, y2 minus y1 over x2 minus x1. Okay, very similar. Okay, so final velocity minus initial velocity over finite time minus initial time. If you compare to slope, that's what this means. So the acceleration is a slope if you draw the velocity time graph like this. So the velocity time graph, then the slope, we take the slope, that is the acceleration, the slope, acceleration, the slope here. Okay. So we can have a positive slope where the slope here is positive. Then you can have a negative slope here. It's dropping, right? Negative slope. So this is a positive slope. It goes like the positive slope, rises from left to right. Negative slope, the line drops from left to right. Okay. And then here horizontal, remember horizontal means zero slope. So here it is zero slope. Okay, zero slope. So that's what the meaning of acceleration, the rate of change of the velocity with time. Okay. So I have a little note here. The acceleration and the deceleration can be found by finding the gradient of the slopes. Okay. We're going to come across questions using this soon, right? So they can give you a graph and they put in different time zones here, different times, right? And they ask you between which interval is a car accelerating, or between which interval is a car decelerating, and so on. All right. So the positive slope means the car is accelerating. Horizontal line here, it means a constant velocity. The velocity is not changing. Constant, same, moving at the same velocity. In other words, there's no acceleration here. So here, no acceleration. That's what the zero slope means. No acceleration here. And then if it's here, from this interval to the end, it's decelerating, means the acceleration is going down. So deceleration here. So the car is slowing down till it gets to zero here. Okay. So those are the three zones, 1, 2, and 3. When they give you a graph that you can use to answer questions, right? And then if you for the same graph, if you want to find the displacement or the total distance covered, it's basically the area. So the distance traveled is the area under the graph. So if I want to find the distance traveled from this point here to, let's say, this time, up to here, from 0 to maybe, let's say this is 5, then I have to find the area under this line from up to this point. Then that would be the distance traveled or the displacement. Okay. If I want to find the total distance traveled from here all the way to that end, then I have to find all the area under the line between those two endpoints. So everything here, that will be the total displacement or the amount of distance traveled by the object and so on. Okay, so the area under the graph is the displacement. Okay, so that's what you should remember when they give you a graph like this. As I said, we'll see some questions very soon, how to apply this. Okay. Okay. All right. So before I go on to this one, let me see what we have here first. Okay, so let's look at what I have here before I move on to the next one. Okay. So I have positive slope means the car is accelerating. That is, the velocity is increasing with time. Zero slope means the velocity is constant. That is not changing with time. And negative slope means the car is slowing down. That is, the velocity is decreasing with time. Okay, so I said that already. Okay. All right. Yes, what I wanted to say is that it's good to know the difference between displacement and distance before we even mention these things here. A little bit more explanation on that. Let's say that I have an object that moves from this point here, this is 0, to, let's say this is 10, let's say 10 meters, right? So the object moves from here, 0 is a starting point, and then moves all the way there, 10 meters away. Now, the distance covered by this object will be 10 meters, right? So the distance is 10. 10 meters, that's the distance covered, right? If it moves back to its starting point, then the total distance covered will be 20 meters, right? 20 total. Distance will be 20 meters. That's the total distance covered. Okay. But what will be the displacement? What will be the displacement? Will anybody give me the answer for displacement? What do you think will be a displacement? if I ask you about displacement? Anybody knows the answer?
We need the function for velocity to get displacement.
Okay, no, for this particular one, it moves here and then back. We said that the distance is 20, right? But distance is different from displacement. The distance, the direction is not important, right? It's a scalar quantity. So I just have to add up the lengths. But when talking about displacement, direction is important. Direction is important. So if it starts here and moves towards the right, we're going to use plus and minus to indicate the directions. So it moves towards the right, then it's moving in a positive direction. So it means that it went 10 meters, positive 10. And then it's moving backwards to its original point. So it's traveling in the opposite direction. So it's another 10 in opposite direction. So it means that plus negative 10, opposite direction, because the direction is important in displacement. So if you put this together, you have 0. So 0 meters for this particular one. So the displacement, how far it is from its starting position, it's 0. Displacement of 0, even though it traveled a distance of 20 meters, the displacement is 0. Okay, so that is the difference between displacement and distance. The direction is important in displacement. You got to take into consideration the sign. Opposite direction, it's negative. If you're moving to the right, if to the right is positive, to the left is negative. If it's moving up, it's positive. If it's moving down, negative, right? So you have to think about displacement like that. Positive direction, negative, moves up, positive, up, down, negative. Okay. So that is how you think about displacement and then distance. Okay. All right. So on this screen here, I have some of the units that you should also know. So the unit that you should know of. Okay. So no work, the unit for work is joules. The unit for work is joules, right? And then the unit for force, as I said, is newtons. Know some of these units. Velocity, the unit is meters per second. It's always per second, per something, you know, but the SI unit, what we call it, SI unit is meters per second. And then we measure time in seconds. When you're working with SI units, it's in seconds. Okay. All right. So know some of the units. All right. So now let's look at forces, application of vectors. Okay. And we also said that, we already said that force is a vector quantity. It's a vector quantity. So direction is important when you have forces. Okay. So look at this question here. Now, you can be given a question in which they can ask you to find what you call the resultant force. The resultant force is basically the net force, right? Or what we call the effective force acting on the objects, the net force. Okay. So to find resultant forces, you always have to take the direction into consideration. If it's moving up, it's positive. If it's force acting down, it's negative, right? If it's moving towards the right, sorry, the force acting towards the right is positive. If acting towards the left is negative, and so on. Okay. So think of like pull or tug of war when you're dealing with forces. Okay. So the first one, we have forces acting in the same direction. They act in the same direction. So I put here key points here. If the force acts in the same direction, you add the forces to get a resultant or the net force on the object. If the forces are acting in opposite directions, you subtract the forces to get the net or the effective force on the object. Okay. So if you come back to this diagram, you have 2 newtons acting in this direction. So this is moving in this direction. And then you have 1 newton in this direction. So the effective force or the net force on this object, since they're acting in the same direction, it's like pulling. So their forces will add up. They're helping each other to pull. So here, the effective force is 1 plus 2. And that gives you your 3 newtons here. Okay. And that's the net force or the effective force. Okay. So the object is going to move towards the right side. In other words, towards the east, in the eastern direction. Okay. 3 newtons east. Okay. If we take this one here, let's look at this first before we look at the middle one. Now, for this one, the force 2 newtons is acting towards the left side, so towards the west, and 1 newton acting towards the east, right? So they're acting in opposite directions. Opposite directions. So the forces are acting in opposite directions. You have to subtract the forces, and then the one that's bigger will win. You know, so 2 minus 1 is like a tug of war. Whoever is stronger wins. So this is 2 minus 1, opposite directions, which gives us 1. So that's a 1 newtons. And this one is acting, because the 2 is bigger, it's acting in this direction. That's why it's in this direction. So 2 newtons towards the east, sorry, towards the west. It's acting in this direction. In other words, the object is going to move in this direction with a force of 1 newton. Okay. So the key point, opposite directions, subtract same directions, add up the forces, okay, to get a net. Okay. So I have a couple of examples here. Sorry, let's go to the middle one before we practice this one. So if you look at the middle one, again, you have 2 forces acting up, right? So 2 forces acting up. So the 2 forces are acting up, it means they're acting the same direction. So what you have to do is to find the net force in that direction first.
Add them.
So yes, we're going to add them. So for this direction here, the top part here is 1 plus 0.5 newtons, same direction. So the effective force in this direction, it will be 1.5 newtons acting in the north, right? Then this one's acting down, opposite direction, towards the south. So since now this up and it's acting down, you have to subtract. So you have 1.5 minus 1.5, and then you have 0 newtons. So it means this object, the force on it is 0, you know, for same force in opposite directions. So the object is not going to move. It's going to stay where it is because there's no net force on it. Okay. So you could be asked to calculate net forces like this. Okay. So with that said, let's do the quick practice on this one. All right, so can someone tell me the net force for the first one? This one.
5.
5, good. So opposite direction, which direction?
East.
Left or right?
Right.
Look at it again.
So it goes to the left.
Yeah, because the way the bigger force is.
Okay.
So it's 10 minus 5, opposite
Oh,
direction.
it
So
will
10
go-
minus 5, which is 5, yes. We
Okay.
subtract newtons, but it's moving where the bigger, because this one is going to pull. It's stronger.
Right.
It's like stronger, so it pull
Stronger.
towards, yeah, so towards the left, or let's say that will be north. This is west, right? So we can say towards the west.
Okay.
Good. Think of tug of war. All right, let's call this number 2. So what would number 2 be?
30.
30, correct. Because it's like in the same direction, they're pushing. This one is pushing, this one is also helping out. So it's 10 plus 20, so it's 30 newtons. And this will go towards east, towards the east side, so east. Correct. And then what about this one? Let's call this 3.
Is it 20?
20.
Yeah, 20.
To the
Up or
south.
down? South, correct. So opposite direction. So 30 minus 10. So that'll be 20 down. So that is Newton's south. Correct. And then what about this one?
5 south.
5 south. Okay, let's see. So you found the net force in this direction. So you're going to, since this is same direction, so together this will be 20 newtons down, right? And then this acting 15 up. So it means the opposite directions now. So it will be 20 minus 15, which gives us 5 newtons, but it's acting down, so south, correct. Perfect. Yeah. So these are some ways they can ask you questions on the forces. Okay. Net force or the effective force. Okay, good. All right, great. Any questions on this? I have one more example that I want to give on that. Okay, so far so good. Okay. All right, so let's look at one special case. Okay. So the one I want to put up is this. Let's say if a force is acting here, this direction, let's say you have 6 newtons in this direction. I have another force acting down here. Let's call it, let's say 5 newtons. A force acting here. Let's make it 10 newtons. And a force acting in this direction. I'll make it 5 newtons. So the force acting on this object here. So the question is, in which direction will be the resultant force? We want to find the direction of the resultant force.
Would it be north?
Northeast. Okay, said northeast, right? So it means somewhere here. Okay, good. You're right. So direction of the resultant force. Okay. So when I give you a question like this, as again, you find the effective force or the net force in the horizontal direction and then the vertical direction, right? So for this horizontal direction here, the net force will be 10 minus 5, right? So it means that the object is going to act this way. No, sorry, I said object. The force is going to act this way with a force of 5 newtons, right? It's going this somewhere in this direction, 5 newtons. Then in the vertical direction, I have 6 opposite direction, 5 down. So the net force will be up here, go in this direction, north 6 minus 1. So the effective force 1 newtons, 1 newton, right? Over here. Okay. So you have 5 pulling. So it's like the object is being pulled by something like this. It's being pulled 5 in this direction, 1 in that direction. So it's going to move. The net force is going in between. It's going to be in between this, somewhere around here, in between the two forces. This is pulling there, this is pulling there. So the object's net force somewhere around in between. Okay, so it's in the northeast direction. Northeast. Okay. So usually we ask a question like this, they'll ask you the direction in which the object is moving. To calculate effective force, that would need more math to do. So they will not go in that direction when it's like this. But you should know which direction, estimate the direction in which the object is going to move. Like that. Okay. Everybody okay with that?
Yes.
Okay, good. So the key is find effective force in a horizontal direction, in the vertical direction, and then the force will be in between those, excuse me, will be in between those forces. Good. All right, so that should be good for work problems on forces. All right, then the other thing is work done problems. So these are some of the physics questions, you know, that you have on the test. General physics that you should be able to do. So this one's about work done. As I said, from one of the formulas, as I gave the formula, work done is equal to force times distance. Okay, force times distance. In other words, if a force moves through a particular distance, then work is done. If the force doesn't move to a distance, then no work is done, right? If the distance is 0, so no work is done. Okay, so keep this in mind. There's a scenario that I'm going to ask you shortly. Okay. So this is a formula that you should remember for work done problems. Okay. So work is amount of energy transferred. Okay. So it's a so when force causes a displacement, work done is positive. When force, so when force hinders a displacement, work done is negative. When it's moving against you, you are doing negative work. But it's moving in your direction in which you are pushing, then you are doing positive work. All right. So note that work is not a vector, but the force and displacement are vector quantities. Right? Force and displacement are vector quantities. So we can use displacement in place of the force and in place of distance. Right? For now. Okay. But in your mind, know that they are different things. But direction is important when talking about displacement. Okay. All right. So there's a question that I'm going to ask right now. I think somewhere in the book as well. Let's say that I have a table. And this is a ground. If I have a chair over here, now I take this chair and I put it on the table. I'm going to put it on the table. Okay. And a child, also a 2-year-old child, also comes and lifts this chair, same chair, and put this on the table. Who has done more work? The child or me?
The child.
Say it again.
The child.
The child. Okay. Someone said the child. Anybody else?
Is it the same?
Somebody else said the same. Okay. Any other answers? You don't know? Yeah, that's the other option, right? I don't know. All right. The answer is they all did the same amount of work.
Yeah,
Same work done. Same work done. This is a question that someone in the book too. Right. Why did you say same work done? Those who say same work done.
Because it is the same distance and the shear weight's the same. So I'm assuming it's the same force.
Right. So same force, correct? Yes. But the distance, the key word is the distance.
Oh,
right?
Yeah.
The same force and the distance, the same, they move through the same distance.
Mm-hmm.
You're lifting the same thing, the distance is the height of the chair, of the table. So this same distance, same force, so the work done is the same. Work done is the same. Yeah. If the distance is 0, if I don't move at all, then no work is done. So it means this is 0, then no work is done. The chair will be the same position. But we all do the same work. Since we're lifted same force through the same distance. The only difference between the two of us is the fact that the child puts in more energy. Energy is different from work. So the child put in the same amount, a large amount of energy to do the same work. So we define energy as the ability to do work. The person's ability to do work. That's what we call energy. Okay. So energy, the ability to do work and cause a change, is what we call energy. Okay. So the child did more, put in more energy to do the same amount of work that I did. So that's one application of what we just done. Okay. Any question on that one? All right, so far so good. Okay. All right. Okay. Now I'm going to add one little one little piece here, and that has to do with different types of energies that we have. Energies. Now but I'm going to focus on two types. One, what we call potential energy, and the other one will be kinetic energy. Energy, potential and kinetic energy. Okay. When you say potential energy refers to the energy that an object has by virtue of its position or its height, right? So energy due to position. Due to the position. That's what we call potential energy. Okay. And then energy due to movement, the fact that the object is moving, it has what we call kinetic energy. So energy due to motion, it's called kinetic energy. Okay. And mathematically, the formula that we use is, so I'm going to use P for potential energy. So the potential energy is equal to the mass times gravity, acceleration due to gravity, and then times height, mgh. When you see G refers to acceleration due to gravity, right? G, acceleration due to gravity. Okay. The value is 9.8 meters per second squared, right? So this is a value for acceleration due to gravity. So if I throw something up, it's going to move with that acceleration, 9.8 meters per second. But for calculation purposes, most of the time, you can approximate to 10. You can use 10 meters per second squared. You know, if it comes up in a question, they'll most of the time use approximation. It's easy to work with 10. You know, they'll tell you approximately this. Okay. So if you know the mass, if you know the gravity, we already know the acceleration due to gravity. If I multiply by that times the height of the object, you get the potential energy. Whilst kinetic energy, let's use K for kinetic energy, will be half mv squared. Half mv squared. So the m is the mass, v is the velocity, right? So 1/2 times the mass times the velocity squared gives you kinetic energy. Kinetic energy. Okay. So this can be used in calculations. Okay. But a common question that is usually asked is the diagram that I'm going to show you. I'm going to draw now. I think we may see it in the question in the book too. It's a question that looks like this. Let's say you have a mountain or a hill, and then you have an object here, a ball rolling down the hill. Okay, right this. So at the top of this hill, this object will have the highest potential energy, right? That's the height, maximum height here. So this is going to have the max potential energy. So max potential energy at the top. If it's not moving, then it means that the kinetic energy is 0. So here we have Ke, let's use K for kinetic energy, is 0 at that point because it's not moving. Rest at my highest height. Now, once it begins to move, then the potential energy is changed into kinetic energy, right? Energy can be changed from one form to the other. You can't destroy the energy, but you can convert it from one form to the other. So the potential energy will be changed to kinetic energy as it moves, as it drops down the hill. So this object at this point will have the total energy here will be both kinetic, it's going to have both potential energy and kinetic energy at that point. When it comes to the lowest level, now all the potential energy would have been changed to kinetic energy. So at this point here, lowest level is going to have the maximum kinetic energy at this point. Since there's no height, the lowest ground level, so all this is ground, the potential energy here will be equal to 0 at this lowest level, okay, because the height is 0. So all this is 0, okay. So remember maximum height potential and maximum potential energy. Lowest point here is going to have the highest kinetic energy. In between is going to have both kinetic and potential energy, and so on. Okay. So this diagram is going to come up somewhere. The same thing can apply to another scenario for this is a pendulum. If you think of the pendulum also is going to show potential energy, kinetic energy, and so on. I'm going to draw that for you to see. Okay. So over here, if I take the pendulum, so if I swing it to this side here, displace it a little bit. So this is a starting point. So this is a starting point. So this is a resting point. Okay, so that's the height. From here to there is already the height. I displace it, so I move it through this vertical displacement, the height, starting in a new position. So once I put it here, it's going to have the maximum potential energy at this point. So max PE, potential energy when I displace it. The kinetic energy at this point is currently 0. If I'm holding it at that level. Once I release it, then the potential energy is going to change to kinetic energy as it swings. So when it gets to its lowest height at this point, the original starting point, then you're going to have maximum kinetic energy here, Ke here, because that's the lowest height. Original starting, that's the original point. So maximum kinetic energy at this point, right? In other words, you have 0, potential energy at this level is 0 because the height is 0. Okay. Then as it swings again, the kinetic energy is going to change to potential energy as it swings. And then it gets here again, this will maximum again at this point. Maximum PE, and then KE will be 0 at that point, and so on. In between is going to both kinetic and potential energy in between, okay, and so on. Here, both PE plus KE, both, okay, all right. So if you see a diagram like this, you should also remember the potential and kinetic energies, how it changes. All right. So those are 2 scenarios that I want you to think about. This one and then the pendulum one. Any questions so far on this? Okay, so I believe it's clear. All right. Good. Right. So we're going to switch our minds a little bit to electricity. Currents. Okay. All right. So there are 2 types of electrical circuits. The wiring, how the wiring is done in any electrical equipment or in the house. So they like these questions too, right? So you have to know what we call the parallel circuits, and then know what we call the series circuits. So those are 2 types, parallel and series circuits. Okay. You should to identify them when they draw the diagrams. Okay. So in a parallel circuit, there is an alternate path to the flow of current if other paths are blocked. Okay, what do I mean by this? If you take this, think like a road. If I blocked the road here, right, the current will flow. Usually the current flows from positive. This is a battery. When you use E, this is a battery here. The symbol represents the battery, okay, plus and minus end. The current flows from positive towards the negative end like this. It goes, So the current is flowing this way. If I block this path here along the R3, the current can still flow, bypass and flow, can bypass. So there are alternate paths to the flow of the current. When you see anything like that, then you are dealing with a parallel circuit. Okay, there's an alternate path if one is blocked. Okay, so some symbols to note, if you see in the diagram, R represents what we call a resistance. We use R in electricity for resistance. So anything that will oppose the flow of current is known as a resistance. Okay, so like a bulb resistors, or it can be like any your fridge, which is be connected here and so on. Okay. Right, so the parallel circuit is very good when you're doing like house wiring. Okay, so if I put my TV here, I basically have a fridge here and something else here. If this line there's a problem with this fuse here, this will still, there's a problem with with this line. The current will still flow. That's why sometimes you have light in one part of the room, and then some other part of the building, there's no light because of the wiring system, parallel circuits. Then the series circuit, there's only one path. So if you block that path, current will not flow again, right? So current is flowing from here, positive end towards the neck around. If I block it at this point, it means that the current will not flow again. And then that's the end. Okay. So this wiring is not good for like when you're wiring a house. Series is not good. You don't want your fridge here, TV here, everything, and it's not too good because one goes off, everything here is going to go off, So parallel helps. So you should be able to identify these diagrams when it's given to you. Okay. So the symbols, as I said, this represents a battery or a cell. If you see anything that is like long line, short line, that's a battery. Okay, usually the long is a positive end and it's like a negative end. You will see the R, that's a resistance or anything that will resist. The symbol is like, if this wiggly symbol, that's resistance. Anything that will resist flow current. If you see a symbol that looks like this, and then like that, this represents a bulb. It's a bulb. Okay. And then when you see anything that looks like this, and then this is a switch. Okay. So if it's like this, it's open, right? It's open. So that's an open form. When it touches the line, so this one touches, let's say touches, then that's a closed form, closed switch. It means you've turned it on. So this is off and this is on, like off and on. Okay, so those are some symbols that you come across in electricity. Okay. Now you should know the quantities and the units that are used in electricity, quantity and units. Current, we use I for current. I is for current. And the unit is amperes. Amperes. So if you see A after a number, you are dealing with the amps, 2 amps or 50 amps, 60 amps, and so on. R for resistance is measured in ohm. Ohm. So ohm is a symbol that looks like the Greek omega symbol, like this. Right, that's ohms. So see 2 ohms, let's say 2 ohms, that means you're dealing with resistance, 2 ohms. Voltage, V, measured in volts. The unit symbol is volts. So if you see 2 volts, then you're dealing with voltage, right? And then watts, power is measured in watts, W. So you see 2 watts, it means that's the power generated by that object or electricity. Okay. So know the symbols. Okay. So what's the relationship between current, resistance, and voltage? Okay. And the relationship is V is equal to IR. V equal to IR. So this is something that you have to remember to work out problems. Current is resistance times the, voltage, resistance times the current. Resistance times the current, that is voltage. Okay, voltage. And this is what we call Ohm's law. Ohm's law. Okay, Ohm's law. So in other words, the voltage is proportional to the current and the resistance. Okay. That's Ohm's law. Then when we say power, power is current times voltage. Current times voltage. So P times V, sorry, VI is the power. VI is the power. Current times voltage. Or you can have I squared R. I squared R. They all represent power. I squared R. Okay. If you know one of them, you can always come out with the other one. It's very easy to remember. And this is how you can remember it. If you know power, you know power is equal to voltage times current, right? We can do substitution. So P is equal to, we know that voltage is the same as IR, current times the resistance. So if I replace the voltage here with IR, what is the voltage? IR times this I, I'll end up with I squared times R. Okay, and that's what we have here. So that's power. P is equal to I squared R. That's how that formula came about. So depending on what they give to you, you can use the formula VI or I squared R. If I know the current times the squared times the resistance, you get a power. If I know the voltage, if I know the current, I can find the power. Or if I'm giving voltage and I give the power, I can find the current. You can play around with this. Two should be known. We can find the third one. Okay. So let's keep this formula somewhere. We'll use it along the line. Okay. Right. Then this takes us to another aspect known as electromagnetism, right? Magnets and electromagnetism. Okay. So let's begin with what a magnet is. I believe we all know what a magnet is, but the physics behind it. All right. So magnetism. So when you take a magnet, there's a force, a field around it where you can feel the force. So this is what we call the magnetic field. We said there's a magnetic field around the magnet, right? This is a mathematical representation of the interaction between the magnetic material and electrical currents. It's represented by the magnetic field lines, which moves out of the North Pole into the South Pole. So this is what we mean. If you take a magnet, it is a magnet. Every magnet has what we call a North Pole and a South Pole. Okay, in other words, if you suspend the magnet on a rope, it's always going to turn around and to align itself in the North and South poles of the Earth, right? That's why I use a magnet, a compass. No matter the direction you turn, it will always align itself in the North and South pole of the Earth. So have a North Pole and South Pole. Now the force around the magnet, which we use the field lines to represent, always moves from the north and then into the south. So the arrow, we point the arrow in like this. It moves out from the north to the south. That's how the forces act, from north into the south. So your arrow should always move out from the north and it should enter the south. If you see any other diagram that doesn't look like this, the arrows are pointing different direction, then it's a wrong diagram. Okay, so be careful with the arrows. From north and then move into the south, north to south, north to south, and so on. Direction of the force. So these are what we call the field lines. The lines I've drawn, those are the magnetic field lines. Okay. So these are magnetic field lines. Okay. And then all the space around is the magnetic field. That's what that's what I just read. Okay. All right. So let's read this here. So it's a magnet. A magnet is any object that has a magnetic field. It attracts ferrous objects like pieces of iron, steel, nickel, and cobalt. The end of a freely pivoted magnet will always point in the north-south direction. The end that points in the north is called the North Pole of the magnet. And the end that points south is the South Pole of the magnet. So like magnet poles repel each other, whereas unlike poles attract each other. In other words, if you bring the north and south together, they will attract. I'm going to show you a diagram soon. And if you put the south and south together, they'll repel. You see, if you put it, your hand will be shaking. You can't put the south and south together or north and north together. They try to move apart. But when you put the south and north together, they'll just attract each other. Okay. And then so what's a magnetic field? The space around a magnet in which magnetic force is exerted is called a magnetic field, right? And as I just explained, the properties of magnetic field lines. The magnetic lines of force originate from the North Pole of a magnet and end in the South Pole. 2, the magnetic lines of force come closer to one another near the poles of a magnet, but they are widely separated at other places, right? So as it can be, you get closer and closer, that's what we're saying. You get closer, but as they go, it becomes wider, they separate out. You know, I didn't draw my diagram too clearly, but they move out and they become wider as you move away from the poles. Okay. And point number 3, the magnetic lines of force do not intersect. So they don't intersect. And then 4, when the magnetic compass is placed at different points on the magnetic field line, it aligns itself along the tangent of the line of force at that point. That's, you put a compass along each of these lines. Let's say compass here, it's going to be, the pointer is going to point like at, it's tangential to this. When you put a compass on those points, the pointer is going to like tangent to the field lines. Okay, great. So as I just explained, this is a good diagram of what I've just spoken about and I drew. Okay, the direction, very important, arrows, north, south, you know, and then wider as you get away from the North Pole, the widens. Okay. Okay. So the same diagram here. Okay. All right. Good. So what's the interaction? How do the magnets interact? Now, for the magnets, when you bring the North Pole together, you bring the North Pole and the South Pole together, this will happen. So North and South poles, they interact. Okay. So the field lines will be like this. The North moves, the field lines move out of the North and into the South, move out the North into the South. Okay. So yeah, this attraction. So that's a force of attraction. If you see this diagram, this is the attractive forces. This is how it looks like. Okay, North and South poles. Okay. For repulsion, when you bring North Pole and North Pole together, or South Pole together, the field lines will not, they'll move away like this. So it moving out of the North, it's not going to enter the North here. Okay, decide repulsion. There's a space in between those fields where they're repelling each other. Okay, so it doesn't cross, like it doesn't move from the North to the South like this one. Okay, they push themselves apart. Okay, so you have to know these two diagrams. You know, when they draw, you know which one is attraction and where they repel. Okay, if I bring South and South together, it will be similar to this one as well. Okay, so this is how the magnets fields look like. Okay, any questions on that one? Okay, all right. So this takes us to what we call electromagnetism. Electromagnetism. So electromagnetism is a study that involves the use of electricity to create a magnet and vice versa. So you can use a magnet to create electricity, and you can use electricity to create a magnet, right? So electromagnetism describes the relationship between electricity and magnetism. Electromagnetism works on the principle that an electric current through a wire generates a magnetic field. When you wrap a wire around a metal object and then pass current through the wire, that object becomes magnetized. Likewise, when you move the magnet within a coil, it generates current or electricity, right? So this is a summary of what I'm going to talk about. Okay, so this takes us to what we call what is a solenoid. Because solenoid, I'm going to show you what a solenoid is shortly. This is what a solenoid looks like. Okay, if you take a coil, you take a wire and then you wrap it, let's around a metal like this, form a coil around it. This is what we call a solenoid. You form what we call a solenoid. Okay, so the coiled wire is a solenoid. Okay, so this is a very simple experiment that can be done in the house. You see the wire coil like this, connect a battery here, and then put a nail, which is like it's an iron, made of iron, into the middle of this coil. You create a magnet. The nail here becomes a magnet. You can attract metals with it. So this is an example of electromagnetism in progress. Okay, the nail becomes a magnet. Okay, So this is another picture of it. Battery, ion, coil. The nail is going to become a magnet when it's connected. Okay. So you should have an idea of this diagram in your mind for questions. Right? Usually they'll draw it like this. You see something like this, then they'll draw it. So that's a battery. And then you have a coil. You see this diagram, and then they put in something here, a metal. Then you know you're dealing with electromagnetism. This metal will become a magnet. Okay. And then vice versa. You can also generate electricity using a magnet. And that one will look like what I have here. Okay. So if you create a coil or a solenoid, you have a solenoid. And if I connect a bulb over here, so that's a bulb. And then I have a magnet. I bring a magnet here and I move it in and out. So then this time it's a magnet. If I move the magnet in and out of the solenoid or the coil, this bulb will light up. The bulb is going to light up, right? So there's a magnet here moving in and out. This bulb will light up because it creates a current that flows through the coil and lights up the bulb. So to light up, if you move it in and out of the coil. Okay. So that's how you can use electricity to create magnets, and you can also use a magnet to create electricity. That's what I call electromagnetism. Electromagnetism. Okay. And this is some people are making money out of this. You know, like the bicycle, the bicycle light, that's how it works. As the person paddles, there's a coil in there. So as the person paddles, there's a magnet in the coil that is turning around. So it's moving the magnet in the coil. So as it moves in the coil, it generates electricity that ends up lighting the bulb of the battery. You know, the solenoid in there. So once the person stops paddling, then it goes off. That's why the light flickers as they paddle. That's an example. Then another example, it used to be on the TV some time ago. I don't see it these days, but there's a torchlight that they advertise that you don't need batteries forever. Okay. So the same way, it has a solenoid in there, and there's a magnet in. So it's a shake. You shake it, and then it lights up. Shake, it lights up. So you don't need batteries for that one. You just have to shake it. It creates electricity in the coil, and then it turns on, lights up the bulb. You know, it used to be advertised on TV some years ago. So shake it and light up. Yeah. Okay. So that's how the solenoid works. So know the diagrams that I've just drawn. Okay. So let's go back here. So I said that what's the solenoid? A solenoid is a long coil containing a large number of closed turns of insulated copper wire. A magnetic field is produced by the current carrying the solenoid. The strength of the magnetic field produced by the current carrying the solenoid is directly proportional to the number of turns. So that's something you have to know. It can ask you, how can you increase the strength of the magnetic field? So it means you can increase the number of turns and then the strength in the solenoid, direct proportional turns and the strength. So the more coils that you have, the greater the magnetic field that you create, you know, and also the more current you can also create. It's also depending on the nature of the coil. So depending on the material of the core, whether it's iron, nickel, and so on, can also affect the strength of the field that's generated. So when the soft iron rods are used as cores, they produce the strongest magnetism. So soft iron rods produce strongest. Okay, so that's an example of the core material if you use can produce a strong one. The solenoids are used to make electromagnets, as we just said. And then we just said, what's an electromagnet? When electric current flows through a soft iron rod placed inside the solenoid, a temporary magnet is created. It acts as a magnet only so long as the current is flowing in the solenoid. This combination of solenoid and a soft iron core is called electromagnet. So an electromagnet therefore consists of a long coil of insulated copper wire around a soft iron core, right? And these are some of the uses of electromagnetism. You know, using cranes to lift heavy metals, use electric bells, radio speakers, microphones, dynamos, electricity, generate electricity, store memory on computers, generate pictures on television screens, and then MRI. These are all uses of electromagnets. You know, the electronic equipment, they contain these things. Okay. But if you forget everything, remember the diagram. Okay, the diagrams that I've drawn. Okay. All right. So any question on electricity for now? Any questions on electricity?
No, thank you.
All right. So far, good. All right. Great. Okay. So try and finish this up, and so we can answer some questions to see how to apply them. All right. So the next one, I want us to think about some chemistry too, some chemistry topics. And this is organic chemistry. Organic chemistry. Now, organic chemistry, I don't know how many of you have done that, but we can classify organic compounds as what we call alkanes, alkene, alkyne, alcohol, carboxylic acids, esters, aldehyde, ketones, and ethers, right? You should know how to identify this in questions. Even if you don't done organic chemistry before, I'm still going to help you figure that out now. Okay. So, but when you do organic chemistry, you're talking about carbon compounds. It's mainly carbon compounds. So let's say you have a carbon joined to carbon and so on with hydrogen around them. So those are carbon compounds. Sometimes you have oxygen somewhere or have nitrogen somewhere. Okay. Then you're dealing with organic compounds. So the body cells, our body contains organic compounds. Okay, so carbon compounds, you know, with hydrogens. You may have oxygen or nitrogen or phosphorus and so on somewhere, but mostly it's carbon hydrogen compounds. Okay, and alkanes. How do you define alkanes? Alkanes are compounds that have organic compounds that have single bonds in them, single bonds. You always remember that carbon, when you take carbon, carbon can have 4 things around it all the time, right? Maximum of 4 things. So I have a bond here, bond there, bond there. In chemistry, carbon needs four bonds around it, or 4 items around it, atoms around it. So all the 4 can be together like this, single like this, or sometimes I have a carbon that with 1, 2 bonds between another carbon, but then you have 2 other bonds. It still makes it 4. So 1, 2, 3, 4. 4 bonds. 1, 2, 3, 4. So each one 4, 4, 4. So it can double, or I can have all the bonds 1, 2, 3. 3 between maybe carbons, then 1 more left. You know, so it can be 3 and 1, or 2 and 1, 1, or 1, 1, 1, like this. These are all possibilities that carbon can form bonds, right? So when you talk about alkane, the first one, alkane, we are talking about where you have only single bonds. You don't have double bonds. So you have a carbon with single bonds. So this one, for example, I'll get rid of this one here. You have a single bond here, CH4. It looks like this, C and then H. So this is single bond. All right. I can draw another one. Let's say different one. C, we have 2 carbons. And then I can draw hydrogens around it. So again, these are single bonds in between. So if I see anything with single bonds like this, you call it an alkane, single bonds, single carbon to carbon bonds, alkane. And this is an example that I've drawn here. Okay. How can you identify an alkane? It's very simple to identify an alkane. You can use this formula. It's going to work out for you for all the alkanes. But when they give you a compound, you don't have to draw the whole thing. You don't have time to draw the whole thing. So the formula here, you have CN H2N plus 2. CN H2N plus 2. That's how you can identify an alkane. All right. So if I give you something like C, let's say 4, H, this will be 10. Just by looking at this, I know this is an alkane. Why? Because in hydrogen, the number of hydrogens here is always 2 times the number of carbons plus 2, right? 2 times the number of carbons plus 2. Then that gives me an alkane. Then I don't have a single bond in this. Okay, another example. If I have C, let's say 50, H 102, you're not going to have time to draw all the 50 carbons and then show hydrogens. That's waste of time. So just look at the hydrogens, find out whether it's 2 times the number of carbons plus 2. When I come here and look at this, 50 times 2 is 100, 100 plus 2, that is 102. So this is 2 times times the number of carbons plus 2. So this is an alkane. And we have a single bond if I draw this out. Okay, so you can use this formula to determine what you're looking at. Okay. When it comes to the alkene, alkene has double bonds. Alkene have double bonds. So alkene is going to have, like as I said, 2 double bonds like this, and then the hydrogens will be around 8. Okay, 4 bonds for carbon. So this one here, this how it looks like, C2H4. So this C2H4. So if I see this, this is an alkene, right? What's the relationship? I can use the formula. This is Cn. The number of hydrogens is 2 times the number of carbons. So it's 2n, Cn2n, right? So they give me a large molecule. I don't have to draw all the molecules because there'll be no time to do that on the test. So quickly, look at the number of hydrogens and compare to the carbons. Is it 2 times? Yes. If I have, let's say C50, H100. This is 2 times that. So this is 2n, 2 times the number of carbons. So this is an alkene. ENE, alkene, double bond. Okay, and so on. Okay, C40, H80. This is 2 times the number of carbons. So it's an alkene. You can identify them by thinking of the formula. Okay. Then we have alkyne, YNE at the end, alkyne. These are triple bonds, So this is a simple example, C2H3. Single, these are triple bonds. It's alkyne. So example of alkyne as we have here. So C1, 2, 3, and then this is 1 hydrogen here, 1 hydrogen. So that's this one, C2H2, right? And the formula for this is Cn, H is 2n minus 2. So it's 2 less than twice the number of carbons for the hydrogen, all right? So an example, if they give a big molecule, let's say C50, H 98. I can look at it and I'll know what group it belongs to. 2 times 50 is 100 minus 2, 98. Right? So it means that this is an alkyne. You have triple bond somewhere in the molecule. So you can use these formulas to help you. So alkane is like in the middle. Alkane is the middle, like CN, H2N. If you add 2 to it, you get an alkane. If you subtract 2 from it, you get an alkyne. You know, that's the way you can remember this formula. Okay, right. And then the other one that you should identify is an alcohol. Alcohol, should identify alcohol. So alcohol, the formula for the alcohol is CH, is ROH. ROH. What do you mean by the R? This R here. In organic chemistry, when you say R represents carbon chains. Yeah, I'll give you an example here. If I write CH3OH, this over here, CH3 here, this is what we refer to as the R group. The R group. You know, the actual word is called alkyl. Alkyl group. The R group is alkyl group, R. We use R to represent carbon chains. So I can write this as ROH to replace all this here, ROH, okay? Because the R can change. I can have 1 carbon, I can have 2 carbons, 3 carbons, and so on, right? So it can be, let's say C3, 2 carbons, CH5OH, okay, if I have 2 carbons and 5 hydrogens. This is your R group. Okay, that can change. So every alcohol has the R group and OH. See the carbon chain and the OH somewhere, then you know you're dealing with alcohol. So if I see this is an alcohol, R group with OH, alcohol. Okay. Then you have the carboxylic acids. Carboxylic acid, you're going to have R group with OOH. You see OOH at the end. Then you're dealing with what you call carboxylic acid. Carboxylic acids. Okay. If you expand it, it will look like what I'm going to draw here. So carboxylic acid, let me draw this one here. CH, so it's like C, then you have hydrogens around it. And then this will be C, then double bond on oxygen, and then OH. This is how it looks like, the carboxylic group. COO, this is a COO end here, a COO. And it's a CH3, like this one. Okay, so it's like CH3, that's this part here. And then this C double bond looks like this. That's how it looks like. And if you combine all this, we can just write CH3, COOH. That's what this part represents here. Okay. So we see the CON according to the Q group, Q. At the end of our group, then you know you're dealing with carboxylic acid. Okay. Then you have the esters. The esters are compound formed between an acid, carboxylic acid and alcohols. Carboxylic acid and alcohols form what we call an ester. So that's going to look like this. Carboxylic, so you have ester is equal to carboxylic acid plus the alcohol. That's what gives you an ester. So anything that smells good is formed from an ester. It's an ester. It's an ester. Like nail varnish, nectar, you know, things that taste sweet, you know, they are all esters from carboxylic acid and alcohols. Okay. And the formula is ROOR. We have COO between 2 R groups, as you can see here, ROOR. R and then CO. So this is the R group. That's another R group here, and then CO in between, 2 R groups. Then you have an ester. Okay. Now we come to what we call the aldehyde. You have an R group, and at the end you have CHO. CHO. So this is the R group, and then that's CHO end. And the R group is this. Okay. Then you have ketones. Ketones, you're going to have R group, which is this, then CO in between, and then an R group, like this. Okay. Or if I want to draw it out a little bit, I can say CH3, then you have carbon, then if you see this here, and then CH3, this is the same thing. CO in the middle, holding on to 2 R groups. Then you're dealing with the ketone. You have a ketone. Okay, this is the same thing I've drawn here. CO in the middle, holding on to 2 R groups. Okay, ketone. Then you have ether. Ether is oxygen holding on to 2 R groups. R group, oxygen, R group, they have what we call an ether. Okay, so these are the groups that you should be able to identify if they give you in questions. Okay. So we'll see a couple of examples.
So Professor,
Yes.
they will give us the example of the organic compound and we will have to write the name of the organic compound.
Yeah, they can ask you which of the following group does it belong to, right?
Okay.
They'll give you the diagram. Okay, let me just quiz you like a few questions. I'll make up some questions right now. And then you tell me which group. So let's say I have C, let me see, 20H. Let's say I'll make this 42, C20H to 38, C20H, and then 40. Okay. Then I'll do CH25OCH3. And then I'll do another one, C3H to 7COOH, 3H7 CHO. Okay, let's these few ones here. Which group would the first one belong to?
Alkane.
Yeah, alkane. Alkane. It's an alkane. Because 2 times 20 is 40 plus 2. So that's this. So it's an alkane, right? And then this one will be
Alkane.
alkene. Alkine, right? The YNE.
Yeah, why?
Yeah, so alkynes, triple bonds, right? Because 2 times 20 is 40 minus 2. 38, yeah. So it's alkyne. And then this one will be
Alkenes.
alkenes, ENE, double bonds. Okay. And then what are this one? ROR. Oxygen holding on to R groups. So that'll be ether.
Oh,
right?
ether, yeah.
Ethers. So it's an ether group. Oxygen, this is R, oxygen in between. Okay, then this one will be which group? Yeah.
That would be carboxylic, whatever.
Carboxylic.
Yeah,
Carboxylic. Right, that's the cool group, right? Cool. COOH. So this is a carboxylic compound. Acid. Okay. So that's how the attribute group belongs to. And then this one, CH37. Then you have CHO at the end.
Aldehyde.
Aldehyde. Good. So that's an aldehyde group, and so on. Aldehyde. Okay. Let me add one more. C2H5 5OH. Which group would this be?
Alcohol.
Yeah, there's some alcohol. Alcohol, correct. C2H2OH and ROH, alcohol. Yeah. So that's how they give you the formula or the compound, and then they can ask which group does it belong to, which class. Yeah. All right, makes sense, everybody?
Yes.
Okay, good. All right.
Professor, I had a question.
Yes, go ahead.
How much of physics will it be on the test? Do you know?
I don't know the percentage of hand, but they
Oh.
have quite physics, number of physics too.
Okay.
Yeah. Yeah. Right. Okay, so now let's narrow down to, let's come back to some biology. Some biology to relax our brains a little bit. Okay, so this is something that we know already, so it's going to be fast. Let's start metabolism. So we know that metabolism is a process by which organisms build up or break down substances, right? And there are two types. We have anabolism and catabolism. So anabolic process, what's anabolism? We know that anabolism is a synthesis of complex substances, right? Synthesis is the production of more complex substances by combining two or more simpler substances. So you have a simple substance, you put them together, and they form a complex one, right? So that's anabolism, it's building up, which is synthesizing, right? So example of that would be glucose. You have glucose, if you change to glycogen, that's anabolism. You have simple glucose to complex glycogen, right? Then catabolism, as we know, is breaking down. This one you are breaking down. So complex substance broken down into simple ones. So I have a complex and I break it down into simple substances, right? So example, like going backwards, glycogen broken down to glucose. That's the catabolic process. So remember anabolism and catabolism. Anabolic, you build up. Catabolism, you break down. Okay. So when we want to apply this to some processes in our body or in living things, I want us to think about photosynthesis and respiration. Now, photosynthesis is the process of making food, or the process by which the plants make their food, in other words, glucose, from using sunlight, right? And the sunlight energy. And then they need carbon dioxide and water to make their food. You have to know the formula very well for photosynthesis. I'm going to show you, how to remember that. And then respiration. If you know one of them, you know the other one. So photosynthesis, since you're making glucose, you are building up from glucose from carbon dioxide and water. Is an example of anabolic process. You're building up, right? Forming something complex. Whilst respiration is an example of catabolic process. Respiration, you break down your glucose. You break it down. So that is an example of a catabolic process. Okay. So we'll come back to this diagram again. But let's look at the outline for respiration. Respiration, which is a catabolic process. I want you to remember that respiration is made up of three main stages. One, the process called glycolysis. For now, you don't need a detail for the test. If you're doing physiology, anatomy, or biochemistry, then you have to know the details very well. But for this test, just the quick overview. It's made up of glycolysis. That's the first process in respiration. Glycolysis, where you break down glucose, is broken down to what we call pyruvate, right? Pyruvate. Okay. And then the second stage is known as the Krebs cycle, or some people call it the TCA cycle, the tricarboxylic acid cycle, the same thing, TCA cycle, TCA. tricarboxylic acid cycle. Yeah. That's second stage. And the third stage is what we call the electron transport chain. So there are 3 stages in the process of respiration: glycolysis, Krebs cycle, and electron transport chain. Okay, so remember those 3 stages. There's a question that asks you, which of the following involves all the 3 stages, you know, and they have glycolysis, Krebs cycle, electron transport chain, and they have respiration. So respiration involves all the 3. Okay. So during the glycolysis, the pyruvate that is formed goes through the Krebs cycle. But before it goes through this, oxygen has to be present. So for this to occur, you need oxygen. Needed for the pyruvate to go through the Krebs cycle, right? If there's no oxygen, then the pyruvate will go through with the process called fermentation, right? So here, oxygen is needed here. No oxygen, then this one will go through fermentation. It goes through fermentation. Okay. In other words, it's going to lead to, in our body, it's going to lead to what we call the production of lactic acid. Lactic acid. And lactic acid is what causes the muscle cramps. When you're running, you don't have enough oxygen in the legs, in your muscles, then quickly the pyruvate is changed to lactic acid. It causes cramps, and you have to stop and rest your arms, your legs, you know. And as you rest, the blood flows back, oxygen comes in, and then the lactic acid will then be changed back to pyruvic acid again, and then to go through the Krebs cycle, you know, when oxygen is present. Okay. So these are the 3 stages of respiration. Okay. And at the end, you're going to produce ATP, you know. And during these stages, there's something known as NADH, as you can see here. They are formed along the line, NADH, they are formed during the processes. And the NADH, you call them reducing substances. They go through what we call the electron transport chain. And then in the electron transport chain, that's where you have a lot of the ATPs produced. Most of the ATPs are produced here, a lot, electron transport chain. So without the electron transport chain, we cannot produce a lot of the ATPs. You know, there are about 38 ATPs in all that are produced, you know, through the process of respiration. So what happens is that if this electron transport chain is poisoned, then the person is going to die fast. You know, so some of the lethal injections, the medication they give, it poisons the electron transport chain. And that's what, so the person cannot produce ATPs, and the person ends up dying. So that's the overview of respiration. But you have to know the formula, as I said. So I have it somewhere down here. Let's go here. This is a summary of all that I said. Okay. Respiration process that converts energy in food to ATP. You know, it consists of 3 stages. Glycolysis break down glucose through a series of steps to pyruvates. So those are the stages of steps. They have Krebs cycle, also known as citric acid cycle. Pyruvate is changed to acetyl-CoA, what we call acetyl-CoA, which then combines with other chemical substances in this cycle to produce what we call the reducing substances, NADH and FADH, right? And then these will go through the electron transport chain. So electron transport chain. In the presence of oxygen, NADH and FADH pass through the electron transport chain. And the chain is a series of enzymes that generate ATP. So this is where most of the ATPs are produced, right? So that's a summary of all that I just said. And then the formula, which you should know very well. Sometimes they give the formula on a test. You have to identify whether it's respiration or photosynthesis. So let's see if we can memorize this formula. So for glucose, summary. Remember glucose, the formula for glucose is C6H12O6. So if we see that, remember that's his glucose formula. Okay, the hydrogen is always like twice the number of carbons here, and then up to O6. So C6H12O6, that's glucose. If you see this formula, that is glucose. So glucose plus oxygen gives you carbon dioxide and water. Those are the waste products. And the ATPs are produced, right? So this is a formula for respiration. If you balance out, they have 6, 6, 6, 6 here. And so that's a balanced formula for respiration. Know this very well. C6H12O6 plus oxygen 6O2 gives you carbon dioxide, 6 of that, plus 6 of water and ATPs, energy. Okay. Then I said that what happens if there's no oxygen available? If there's no oxygen available, the pyruvate goes to, becomes lactic acid, right? And then, as I said, this causes the cramps. Then fermentation is a conversion of glucose to alcohol in the absence of oxygen. Okay. So that's what we call anaerobic process. When there's no oxygen, they are different anaerobic process. So you produce alcohol through fermentation. If it's a mussel, you produce lactic acid. Okay, good. Right, so with this knowledge, we can look at photosynthesis. Keep this formula in mind. If you know this formula, if you learn backwards is going to be respiration, so photosynthesis. Backwards will be photosynthesis. If you know one of them, switch the backwards, and you get the other one. Okay, so let's look at photosynthesis here. So photosynthesis is over here. So photosynthesis is a process by which plants manufacture their food by utilizing energy from sunlight, all right? And they need water, and then carbon dioxide from the atmosphere. In the presence of chlorophyll, they need chlorophyll. So if there's no chlorophyll, you cannot have photosynthesis. So you need a green color in the plants, in the leaves for photosynthesis. So we have carbon dioxide, so that's CO2, that's the water, H2O, and then the sunlight and the chlorophyll to produce this glucose, and then oxygen is a waste product over here. So look at the formula again. It's like backwards for respiration. If I turn it backwards, and that's respiration. Okay, so memorize one and then turn backwards another one. Okay. So instead of the ATP, then sunlight energy is what you need here. Okay. So that is how you produce, the plant produce their glucose. Okay. So you can see that plants and animals should live in harmony with each other. The plants give oxygen, and then in respiration, we take in the oxygen, and we give out carbon dioxide. So it's like a cycle. One gives off carbon dioxide, the other one takes it in, uses it for. So plants clean the air. That's why if you kill all the plants, then it means that we're going to be in trouble as well. Yeah. So that's the process of photosynthesis. Please know the formula for the two very well. It comes up in questions. Okay. Right. So before I go on to the next slide here, let me make mention of two things here. One, the water from the soil, right, that goes into the plants, goes through a vessel. Plants have vessels, and that vessel that is called xylem. Xylem. So xylem is the plant vessel that carries water from the roots to the leaves. So the plant vessel that carries water from the roots to the leaves. It's called xylem. Okay. Then once the glucose is formed in the leaves due to as a result of photosynthesis, then the glucose goes to storage sites. So from the leaves to other storage sites through another vessel called the phloem. The phloem. So this is the plant vessel that carries glucose from the leaves to the storage sites. All right, so it's downwards. Yeah. So in other words, when the glucose that is formed, it has to be changed to, it's stored at starch, right? The plants store their excess glucose as starch. So glucose is stored as starch in plants. Remember, starch in plants. Animals will store our glucose as glycogen, right? So glycogen in animals, starch in plants. So these are the two vessels in plants. Okay. Good. Great. Okay, good. So this should be enough for photosynthesis and the respiration overview of each of them.
Professor, I have a question.
Yes, please go ahead.
So it's about the first day lecture, about the year. You talked about different parts of the year. So do we have to remember for the exam every parts of the year, or the specific one that you mentioned and gave description, like the tympanic membrane, the middle ear, the inner ear? Those
Yeah, I
kinds
mean,
of.
just those specific ones should be fine.
Okay, because professor,
Yeah,
sometimes it's hard to remember everything because.
I know. Yeah, that's why it's like sometimes you don't want to, like you have to narrow down to certain areas.
Thank
The eye, for example, the eye you should know, and like the key points I mentioned.
Okay,
The ear, if you can, as I said, remember I said if you can remember the function of the cochlea and the semicircular canal, at least for balancing, a cochlea for hearing, that should be great. And then the function of the eustachian tube to balance, the pressure within the mouth and what do you call it, and then the air atmosphere. Those key ones in the ear should be fine with that.
Thank you, Professor.
Yeah, but the eye know that one very well. It's a common thing that they like. Yeah. Okay. Great. So good. So we finished this one. We're almost there. For the science. Okay, this one will be fast. Tropism in plants. Tropism in plants. Okay, so plants also, they are sensitive to external stimuli, right? They are also stimulated by things outside. So tropism, that is what we call tropism. So tropism is a biological phenomenon indicating growth or tiny movements of a biological organism, usually a plant, in response to external stimulus, right? Or response, we can say the response of plants to their environment. Okay, that's what tropism means. And there are different types of tropism. You should be able to identify them when you see them. It's easy to identify them. We can tell from the word. We have phototropism. They have gravitropism, thigmotropism, chemotropism, hydrotropism, right? So just looking at the word can tell you what it means. Right? Phototropism, it means the plant responds to light. They grow towards light, photo, light, all right? Gravi, towards the ground. So gravity, so the roots grow towards the plants. They're attracted towards the plant. Then thigmotropism is plant response to touch. There are some plants when you touch them, then they move away, or there's the plant that claps, the leaves will come together when you touch them. Those are called thigmotropism, the response. Chemotropism, response to chemical. Some organisms move towards chemicals, hydrotropism, movement towards light. Sorry, light, towards water, water, hydrotropism. So the roots grow towards water. So if you put the root somewhere, there's water somewhere, they try to find where the water is in response to that. That's called hydrotropism, and so on. Right. So those are, if you can remember that for questions, that would also be great. The word will tell you. And all these movements are due to the hormone in plant called auxin. Auxin is a hormone in plants that affects growth. It's a growth hormone in plants. Okay, so I have these examples here for you. Different definitions here, examples of tropism. Vines grow, like thigmotropism, vines grow round trees. They touch the tree and then they turn around. That's thigmotropism. Venus flytrap closes when the leaves are touched. These are all examples of tropism. So the word will tell you what it means once you see it. Okay. Sometimes they draw a box. I'm sure we'll see that question. They draw a box. And then they have a plant in there. And then sunlight somewhere here. There's a hole here. You know, and then the plant is growing towards the hole, something like bending. Then they ask which movement it is. Then they give the options. You know, you select. Since it's light, then it's going to be phototropism and so on. Okay. All right, so that should be quite easy to remember. The same thing I have over here, just different diagrams, you know, to help you visualize. Okay, so those are the tropic movements in plants. Thigmo touch, geotropism towards the ground, photo towards light, and so hydro towards water. Okay, and examples. Okay, so that should be pretty much easy to remember, that one. Okay, and then the last on this slide that I have here, that's homeostasis. So just remember, homeostasis is ability of our body to maintain a constant normal environment, internal environment, right? So if the temperature goes up, you want the body wants to bring it down to maintain the normal body temperature of about 37 degrees Celsius, you know, or 98.6 degrees. You know, you want to maintain that. If body's too cool, your body will generate heat. You know, you're shivering and so on. So the body can generate heat to bring the temperature up to the normal and so on. That's homeostasis. The same with sugar levels. Sugar goes down, pancreas will have to produce insulin to help it bring down the sugar levels. You know, if it goes down, then the body will produce glucagon that will bring it up. And you know, those are homeostasis. We want to maintain a normal environment. Okay. And then the person whose name is attached to this is Claude Bernard, right? Claude Bernard, the French physiologist, Claude Bernard. He came up with the concept in 1865. And then the word homeostasis was coined by Walter Brayford Cannon, right, in 1926. So these are some names associated with homeostasis, as you can see here. Okay. All right, so I think this should be enough for homeostasis. You have a receptor is the part of that senses, the component that senses, all right, is a sensing component that monitors and responds to the changes in the environment, all right? And they have the control center. The control center will be like in the brain that translates the message and then creates a response. So the response will be the effector organ. Okay, the organ that brings about the response is the effector organ, okay? And the change to correct these deviations is what we call the negative feedback mechanism, right? So this is some examples that you should think about under homeostasis. Okay, good. Any question on homeostasis? There's one last part I want to touch on for the science, and that will be good for today. Any questions?
No, thank you.
Great, so far. Everybody's fine, happy?
Yes.
I'm talking a lot, right?
Yeah.
Yeah. All right, so we're going to round up with the last part of the science, acid and bases, and then we'll look at some questions from there. Maybe we'll take a quick break and then we'll continue, do some practice on the, and then we'll come to math. Okay, all right, so acid and bases. I'm going to share the screen on acids and bases. Can you see acid and bases?
Yes.
Yes.
Okay, good, great. All right, so that will also be quick. They also like the acid and bases. I'll point out to you. So basically, when you say an acid, there are about 4 definitions, but I'm going to stick to only two main ones. Okay. So acids are substances that produce hydrogen ions in solution, right? They like using this word hydronium. So if you see hydronium, acid produce hydronium in solution. That's also another definition of an acid, hydronium. Okay. Hydronium is H3O plus 3. That's water that has accepted another hydrogen. So become H3O plus, hydronium ion. Okay. So if they use any of these definitions, hydrogen ion or this, you're dealing with an acid. Okay. So this HCl is an acid because there's something that's missing. The arrow is missing here. The arrows didn't appear on this. This should be like this arrow. Let me rewrite this one. So it's like HCl plus H2O. They have an arrow producing, then we have Cl minus plus H3O plus, like this. Okay, there's missing arrow. Okay. So the acid loses the hydrogen ions, the H, and it gives it to the water. The water accepts it and it becomes that. Okay. So the fact that it produces hydrogen ions, that makes it an acid. So this is an acid. And then here, there is an arrow missing here. It can be Cl plus H plus, like this. Okay. So this is in solution. If in solution, usually they put AQ here, aqueous. You can have AQ. If it's aqua, like aqueous, AQ in parentheses, AQ. They have an acid. And this is known as Arrhenius concept for acid. Arrhenius concept for acid. This name here, Arrhenius. Okay. Then we have Arrhenius concept for a base. Arrhenius said that if you have a base, the base should produce OH, hydroxyl, OH ions in solution. So there's an arrow missing here, NaOH, then the arrow. So you have sodium, it releases sodium ions, and then OH minus. So anything that will produce OH in solution, then you have a base. That's Arrhenius concept for a base. Okay. So other example, let's say if I give you KOH. KOH is a base because if you put in solution, the OH will be given off. You have K plus and then hydrogen OH hydroxyl. So once you proceed hydroxyl ions in solution, anything that will produce that is a base. Okay. Right. So if I see H2SO4, H2SO4, this will produce hydrogen ions in solution. So this is an acid. Yeah, an acid. Usually you're going to see the H will be in front, of the radicals, the acid. The OH will be at the end like that. So you should be able to identify acids and bases. Okay. But not all this, but this definition will not fit all acids and bases. So there's another concept known as the Bronsted and Lowry definition for acid and bases. Okay, Bronsted and Lowry, acid and bases. Okay, so let's discuss that to help you find and determine other acids. Now, one of them is ammonium. This one here, again, the arrow is missing. This arrow should be there. It didn't appear on this. The Bronsted said that acids are proton donors. Anything that will donate a proton donors, that's an acid, proton donor. So this ammonium, this is called ammonium ion. Right? The ammonium ion, if you put it in solution, it gives us a proton. The proton is a hydrogen plus. That's a proton. If it gives this off in solution to become ammonia, this ammonia is ammonium. So this is an acid. Okay. So you see this one, it's almost similar to Bronsted, the Arrhenius, very similar. But we come to the base. the base here, Bronsted said that a base is a proton acceptor. Anything that will accept the hydrogen ions or the proton is a base, right? So if I take ammonium, there's arrow here, which didn't appear. So it's NH3. If you add hydrogen ions to this, it becomes NH4 plus like this. So this ammonia. So ammonia is a base because this can accept the hydrogen ion, the proton. Because it accepts a proton, it becomes ammonium. All right, so that makes this a base. Ammonia is a base. Whilst ammonium can give away hydrogen ions. So that is ammonium ion is an acid. Okay, that's his definition. Okay, so this one, you don't have OH anywhere. You know, the OH is not there. That's why it doesn't fit under Arrhenius concept. But it's also a base based on the definition. Okay. So over here, I have some examples of the definitions for Bronsted. Okay, all this here, producing hydrogen ions in solution, hydrogen. So all these are acids, right? And then when you come here, some Arrhenius concepts, OH, these are all examples of that. Yeah. It's a little shifted on this. The formatting changed a little bit on that. You know, but I have this usually like in a table format. Yeah. And then the other one is a Lewis concept, but I'm going to leave that out. Lewis concept, that is, it says electrons, acids are electron donors. They give off electrons like this, but let's leave that out. And then it's a bases are electron acceptors. Okay, acceptors. So if I have Fe, F ion, if ion goes in, becomes Fe plus 2 electrons like this, because it's given off electrons, that makes it an acid. Right? While Cl, like this one here, if it accepts electrons and becomes Cl minus, then it becomes, it's a base. Electron accept as a base. But let's stick to the Bronsted and then the Arrhenius concept for now. We should identify when it's OH, it's a base. When it can accept a proton or give a proton, then you're talking about Lewis, Bronsted-Lowry. Okay. And the typical example of Bronsted-Lowry is ammonium and ammonia, these two. You know, ammonia, that's what fits in there. Common example of it. Okay. Now, for the what you should know about the basis again is the concept of the pH scale, and how to also test for acid and bases. How do you test for acid? The simple test for acid is if you take what we call the blue litmus paper and put in an acid, it becomes red. So acid turns blue litmus paper red. It's a blue paper, put the acid, it becomes red. You have acid. Then what about a base? A base will turn a red litmus paper blue. So if you take a base, it turns red litmus blue. I'm sure it will be somewhere on the other slide, but we can write it somewhere. So a base turns red litmus paper blue when you have a base. Okay, all right. Then we have the pH scale. The pH scale, if you remember that. So the pH scale measures the strength of acids and bases, right? That's what a pH scale does. So it just measures the strength of acid and bases, the pH scale. Okay, so that measures the strength. Strength of acids and bases. Okay, and the scale ranges from 0 to 14, right? 0 to 14. If you look at the scale, 0 to 14. Zero all the way to 14. All right. Now simply pH, we say pH is equal to negative log of the hydrogen ion concentration. If you do this is called hydrogen ion concentration, the symbol, the concentration of hydrogen. Okay, so that's a formal definition for pH, the negative log of the hydrogen ion concentration. Okay, and 0 to 14. Neutral, as we know, is 7. That's neutral pH. Now 0 to 7, that's you have acid here. 0 to 7 is acid. And then 7 to 14, between 7 and 14, that's alkaline or base. Okay. Now remember that as you move towards 14, it becomes more basic. So increasing base or basicity becomes more basic as you move towards 14. So anything, let's say from 10 to 14 is strong as strong base, right? Like 7 to around somewhere 10-ish, below 10, but greater than 7. So that'll be like a weak, somewhere there, weak, and then maybe strong as you go here. And then if you take about, let's say from 0 to about around 4-ish, it will be strong acid. Between around 4 and 7 is going to be like a weak acid, okay, or 5 to 7 area. So acidity increases as you go towards 0. Closer to 0, stronger acid, increasing acidity. Okay, so if you remember this, you can answer questions. You'll be able to answer questions on the pH. Okay, I'll show you one question that you can also get very soon. All right, so that is the pH scale. Now here, this is some of the, they're showing you the strength of some of the substances in everyday life. If you're interested in looking at that to get an idea of pH. Okay, very good. So I have some questions here which I want us to look at, and then I'll round up on this. So it says that if the hydrogen ion concentration of a solution is 1 times 10 to the power negative 5, what is the pH of the solution? We want to find a pH of the solution. If you get a question like this, all that I want you to do, think of the opposite of this number here. And then that you get a pH, all right? Opposite of the exponent, and then you have the pH. Okay, so you're going to have negative of negative 5, and then you have 5. So the pH for this will be 5. That'll be the pH 5. Okay. So mathematically, you have to plug in, and you need a calculator to do that. So they're going to ask you anything that you need to use that. If it's 2 here, then we can do what I did. It has to be 1 times 10 to the power something for you to apply what I did, you know, because there's a reason. Mathematically, it says pH is equal to, say, negative log, right, of what you have here, 1 times 10 to the power negative 5. That's what you're trying to do. This is the same as 10 to the power negative 5. If I take negative log of that, this is what I'm going to get. One of the rules of log, I can bring the exponent down. If you remember your math, I can bring the exponent down, the power rule. So this exponent comes in front. So I have negative of negative 5 log of 10. Log 10 is always 1. And this is 5. So 5 negative is 5. So negative, and this is log 10 is 1. 5 times that is 5. So that's why the pH is 5. Okay. So this will always work out what I showed you. If this is 1, if this is 2, then you need a calculator to do that, which they're not going to worry you too much with that part. So it's always going to be 1 times something, times 10 raised to the power something. Then you can quickly narrow down to the exponents. Okay. Right. So what would be the answer for number 2? What do you think with the answer number 2?
B.
B. It's weak acid. Okay, let's see. So the pH here, since it's 1 times 10 to the power -3, so take the opposite of the exponent. So that's +3, right? So +3, the pH scale is close to 0. So it means that it's a strong acid, correct? Correct. What about number 3? What's the pH? Okay, let me do that one for you. There's one more thing I have to add here. Now here we're going to find what you call the POH. You give the hydroxyl, right, ion. So they give the hydroxyl ion, you find what we call POH. POH is like finding the pH, so it's negative log of the OH concentration. So again, look at since it's 1 times something, look at the exponent here. So the pH here, POH here will be 5, negative of that exponent, so 5. Now, the relationship between pH and POH is this. pH plus POH is always equal to 14. So that's a relationship that if you can put it down somewhere, it's going to help you just in case. So pH plus POH is equal to 14, right? So now I know the POH because of hydroxyl ion. I know this as 5. So if I know this as 5, then it means the pH should be 9, right? Because 5 pH and then 14. So pH should be equal to 9. So that will be this answer here. Yeah. Okay.
Professor,
Yes, please.
that 14, is it constant? It's not gonna change?
It's constant. No, it doesn't change. It doesn't change. There's a proof for that, but we don't want to go into that part. But it's constant. If you add pH to pH or POH of substance, you get 14. You get 14. Good. So that's a cool point. Okay. Great. All right. So number 4.
B.
Is that what, B or C?
B as in David.
Oh, it's B. Okay. All right. Let's see if that is correct. So here we have OH, right? Hydroxyl ion. So we can find a POH. So POH here, opposite of this. So we expect it to be negative, to be 3, right? It's 3 here. So the pH will be 14 minus 3, and then that will be, what do you call it?
11.
That's 9, right? Yeah, 9. So 9, it's towards 7, close to 7. So it's going to be a week.
Professor?
Yes.
40 minus 3 is 11.
Oh, sorry, that's a 9, right? Thank you.
How would it be D?
So
Yeah,
it's
I was
11, yeah.
thinking.
So I guess we are tired now. 14 minus, yeah, that's 11. So 11. So 11 is closer to what do you call it? 14. So it's going to be a strong base. So it's a strong base. Correct. Right, good. So I'm happy you have the idea. Okay. Right. So we made a good time today. There's one last part of this that you should know. I think it's not here. I don't know. Sometimes something's vanish on there. It converts and vanishes. Okay. So one last part that you have to know very well is neutralization. Neutralization reactions. So they give you the reaction, and then you should identify that is neutralization. And it's easy to identify them. One, neutralization basically is acid plus a base. If you add an acid to a base, you have what we call a salt. You form a salt and water. So those are the things that you identify in a reaction: salt and water, and they have acid and base. Then you have a neutralization reaction. Okay. If you don't see these things, then the reaction of neutralization. So example, if I have HCl, hydrochloric acid, HCl, plus sodium hydroxide, which is a base. So HCl, remember, it's an acid, it can give up hydrogen, and the OH base, right? Arrhenius concept. So if you put this together, that's what we call an exchange reaction. Sodium will combine with the chlorine. So you have sodium NaCl. And then you have the hydrogen here and water there. Sorry, and the OH here forming water, H2O. So this is a neutralization reaction. Acid plus a base giving you a salt and water. Okay, that's neutralization reaction. Okay. You see anything else other than that, it cannot be neutralization. You know. One more example, H2SO4 plus, let's say, KOH. This is an acid, that is a base, OH. This can give you hydrogen. So we form a salt. The salt will be potassium sulfate. This will go with that. Potassium sulfate. Usually it's 2SO4 plus water. Okay, if you balance this reaction, so you have 2 here, so this has to be 2. You should have to balance reactions too. So this is 2 here, this should be 2 there. So you have 2 OH here, so that's 2 hydrogens, and a 2 there, that makes it 4. So it means that this also has to be 2. So this is a balanced reaction for that. So this is the salt, and this is the water. Salt here, and that's the water. So that's neutralization. That's the acid, and that's the base. Okay. So you should be able to identify them in questions. Right. All right, good. So this is a good point to stop. Any question on acid and bases, we'll go on to questions, and then we'll do the math part. Any questions on this? So far, good?
Yes.
Good.
Okay, so let's take 5 minutes break, and then we'll come back. It's 11:56, so 12:01, we'll come back and continue. So take a quick 5 minutes break. Yeah.